So in this video, we're going to show how to actually run the linear model. In a previous video, we built this model matrix X, and we realized that this is what's going on inside when we run the linear model. Now we're going to just run it. So you don't actually have to specify X. We use the LM function for linear model. We use the same part of the formula that we used in model matrix, this tilde diet. We put in front of it the y. So we say we want to model the body weight over the diet. And all the information, we say you can go look for it in this data frame called DAT. Finally, we save this to an object fit because there's a lot of information and it makes sense to save it as an object and then to go in and access that information. So one of the functions that can go in to fit and access the information is the summary function. And it prints out a table. So the summary function prints out a table that looks like this. It tells you the call, some information about the residuals, and then down here is the coefficients table. So let's look at the coefficients table for a minute. It gives you a row for every column of the model matrix. So there was an intercept column, and then there was another column which indicated if the mice were fed a high-fat diet. So the intercept, the estimated coefficient was 23 about, and the difference between the high-fat fed mice and the control mice was about 3. So the weights were about a difference of 3. And then the second column tells you the standard error. The third column tells you a t-value. The t-value is this estimate divided by its standard error. And then the fourth column gives you a p-value. It's the probability of seeing such a large t in absolute value. So when the t-value is very large, then the p-value here will be very small. And then this on the side, it gives you stars or dot as an indicator of whether it's below a certain significance cutoff or alpha. So I want to show you, okay, so another function that you can use to go in and get information out of this fit object is coef, which gives you back the coefficients. So I put parentheses on the side so it prints it, and it also saves it to coefs. So the coefs are 23.8 and 3.02. If we remember, the solution to the linear model is x transpose x, this whole thing inverted, times x transpose y. And just to prove that LM is doing the same thing as the formula we saw, body weight is our y, our model matrix was x, and we can write out in R the same as the mathematical formula. Solve is the inverse of x transpose times x, multiply that by x transpose times y, and you get your 23.8 and your 3.02 as a column vector, which we call beta. So I have 3 more ways to look at these results from this linear model. So the first is we didn't even need to use LM to run this, at least to get the coefficients. Remember, we have our split function. The intercept is actually just the average, the arithmetic mean of the control group, 23.8, and the second group is simply the difference between the means. So in this case, we could have gotten these numbers just simply using split and mean. There are more complicated cases where linear model makes more sense, and it's a much better way to represent complex experiments. But it is true that these numbers can be obtained in this simple way. Now, below I have a bunch of code. You don't need to memorize any of this. This is just to make a plot, which I think is helpful in visualizing what these coefficients mean. So I'm just going to draw arrows from 0 up to the average of the chow group. That's the intercept. So this green arrow represents the intercept. I'll draw a line there, a horizontal line. I'm going to draw a second arrow, which goes from the chow group to the high-fat group. And that is this diet HF coefficient. It's the difference between the average in the high-fat group and the average in the chow group. So that's a horizontal line for the mean of the high-fat group. And I'll put a legend on the side, which tells you the green is the intercept and the orange is the diet high-fat. And so the last thing I want to show in this video is that these results that we got from the linear model are actually equivalent to the result we would get from a t-test. So if we remember that coefficient matrix we got from summary, it looked like this. So if we were to perform a t-test between the chow group and the high-fat group and assume that the variance in the two group is equal, and we'll save that to t-test, a variable t-test, we get something that looks like this. So we have a t value of minus 2.052, and if we look closely again at the value in the t column for the coefficients, it was 2.055 also. So the only difference between these numbers is the sign. So here we had a minus and here we have a plus, and this is the value here that I just pulled out. So here's our minus from the t-statistic, and that's just because when you do a linear model, it looks for the difference between the non-reference level and the reference level, so high-fat minus chow. And when you give numbers to t.test, it looks at the difference between the first and the second. So in this case, if you want to get the exact same number, without the minus 1, you put HF first and say, I want to look at the difference between HF minus chow. So there we get plus 2.055.